Well, hello. This is the second part of our thermodynamics note here for the second day. Main equation we'll be dealing with here is Q equals mc delta T, and as we've got down here, Q is the energy transfer. How much energy has been transferred into this object? M is the mass, because you know from trying to just simply heat things up in the microwave that the bigger the object is, the more energy it takes to heat it up. C is the specific heat capacity of the material. Different things are going to heat up at different speeds. The water, let's say we go out to the beach, the water may be 75 degrees. The beach on that exact same day, the sand, might be incredibly hot from the sun. The sand is going to warm up much faster than what the water does. And then the amount of energy necessary is also relative to how much of a temperature change do you want to make. All right. P in all these equations, they say the rate of energy transfer. Well, the rate of energy transfer is the power. How much power? Q is the energy. Delta T is the change in time in seconds. K is the thermal conductivity, and we'll talk a little bit about that. A is the area of thermal conductivity, and that should be easy. The area of how much area does it have to absorb the energy. L is the thickness of material, and that's going to kind of make up the volume. And then delta T is the difference in temperature change again, as we've said. All right, calculating energy transfer. And we've got a lot of things on here for you to see, but calculate the energy transfer when a block of aluminum 80 degrees Celsius is placed in 1 liter kilogram of water at 25 degrees Celsius if the final temperature becomes 30 degrees. Well, they have us list all the knowns here. What are the things we know? We know that the mass is 1 kilogram. That's important. We have to know the mass. They want us to know the specific heat capacity. Well, right now we're giving it to you for the first time. Some of you from physics will remember this, but the specific heat capacity of water is 4,184 joules per kilogram degree Celsius. Change in temperature. Well, in this problem, we're going to take the water from 25 degrees to 30 degrees. So the change in temperature here is 5 degrees Celsius. And then the next part here then is the change in temperature of the aluminum is going to be from 80 degrees Celsius to 30. Now, equations we have. All right. In both cases, we're going to say that the energy that the one absorbs is equal to the energy that the other one takes in. All right. So the energy that the metal block loses is going to be equal to the energy that the water takes in. So in both cases, we can say mc delta T, and over here we can say mc delta T. In this case, this is for the water side, and this is for the metal side. Well, what is the mass of the metal? Actually, I just realized that they don't give it to us. So that's what we'd be finding here. We've got a couple of things we can find. So, first of all, let's fill in what we do know. The mass of the water is 1 kilogram. The specific heat of the water, 4,184. The temperature change of the water we've already found out to be 5 degrees. And then on the other side, we don't know the mass of the metal. We do know that the aluminum has a specific heat of 900. It doesn't take nearly as much energy to heat up the aluminum. And the aluminum is going to go from 80 degrees to 50 degrees. So if we take these two sides and set them equal to each other, we find out the mass of the metal, then the mass of the metal turns out to be 0.47 kilograms. But we still haven't really found out what they wanted us to find out. They asked us to calculate the energy transfer. Sometimes we get a little bit ahead of ourselves. Well, to find the energy transferred, we could find the amount of energy that the water took in. And if we take 1 times 4184 times 5, we get that the water took in a total amount of energy of 20,920 joules. Alright, on to the next thing here now. Calculating energy transfer. In this problem right here, they want us to calculate the energy transfer in a wall section measuring 2 meters by 1 meter by 0.04 thick with a thermal conductivity of 0.1 joules. Opposing sides of the wall section have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. So right here they've given us all of our knowns and unknowns in this problem. What they show us then is we've got to find out what are our unknown values. Well, P, the power. They're going to say the rate of energy transfer, but it's the power. And Q is the energy transfer. So if you look at our two equations, in this case, select equations to solve the unknown values. Well, I could use either one for power, but I've got to use this one for Q. And if you guys remember back to Algebra 2, if you've got two unknowns, then you're going to have two equations. So all we're doing here is the substitution method. We did a lot of elimination method, you did graphing. They're using the substitution method here to solve for these two unknowns. Alright, so we're going to take the first equation and solve it in terms of Q. So if we want to find the amount of energy, we set it equal and we get power times change in time. That's a pretty simple equation we have there. That's just our power, work, and time equation, because this would be the work. From here then, they're going to take this equation and they're going to plug it in for the power. Having done that, if we go back and look at our givens now, we can start plugging them in. I'm going to take a second and do that. Okay, what I've done here is taken some time to go ahead and fill in the missing information that we needed. And what I can see then is that the K was 0.1, the area was 2, the change in temperature is 5 degrees, L was 0.04, and the change in time was 3,600 seconds, 1 hour, which was 3,600 seconds. Well, let's go ahead and find out what that is. So our energy in this case turns out to be, remember Q is energy, 90,000 joules. And that's what they show us here real quickly. Alright, now we're going to talk about two things here called U value and R value. U value is the coefficient of heat conductivity. It's the measure of a material's ability to conduct heat, and that means absorb heat. When we use it as U, it's the power over the area times the change in temperature. All right, sorry about that. It took me a few seconds there. The next thing we're going to talk about here then is R value. It's the thermal resistance, the measure of a material's ability to resist heat. Right? And it's the inverse. All right, so it's just 1 over U. Remember, U is right here, and to find the R value, we just take the inverse of that. Now, what they are going to show us is the bulk of our R value. Right? Let's say you had several things side by side by side. It's kind of like series. They're resistors, all right? They'd be resisting the ability to conduct heat, and you just simply add them up if they're just side by side. And that's what they're showing us here. Calculating R value, we would just simply have them side by side by side. And they talk about the fiberglass, the drywall, the foil, the airspace, and then the brick. And then we'd simply just add them up. Notice that air does have a much higher, air does have an R value, just simply air. Alright, thermal energy transfer by radiation, the process by which energy is transmitted through a medium including empty space, as electromagnetic waves. Stefan's law, all objects lose and gain thermal energy by electromagnetic radiation. Everything puts off radiation. We lose heat because we radiate heat. The heat you feel coming off your body after a football game is radiation. It's radiant heat. It's not in the form that's dangerous to anybody, but it is a form of radiation. Right? And then here's our equation down here. P is, again, the radiated energy or the power. Stefan's constant. A is the area. And then the T's are going to be the temperatures. Notice this to the fourth. Alright. Prior to dressing for school, a student watched the morning weather to decide what clothes to wear. The bedroom is 65 degrees Fahrenheit and the student's skin is 91.4 degrees Fahrenheit. Determine the net energy transfer from the student's body during the 15 minutes spent watching the morning weather. This is why if you get a lot of people in a room, there is energy that's radiating off you. There's radiant energy and the room's going to heat up. Well, in this case here, they're giving us all the known values. The area, 1.3, they're telling us of the person. E is the emissivity constant. All right, skin, this will be important, is 0.9. Stefan's constant. This is always going to be the same. It's constant. All right, bedroom temperature, skin temperature, and then the change in time was 15 minutes or 900 seconds. Okay, the way we go about doing this is we've got to list our unknown values. And again, we have two variables here unknown. So we have to have two equations. We're going to use our power equation, and we're going to use our energy equation using power and change in time. So the first thing we're going to do here, to find this energy, I know the change in time is 15 minutes. How am I going to find the power? Well, I can use my power equation, and what we do here then is we go about finding it. We convert the 91.4 degrees Fahrenheit and 65 degrees Fahrenheit into temperatures here. So we've got these in Kelvin. It's important that we convert these into Kelvin. And in physics, which some of you haven't taken, we've learned that whenever we're going to do comparisons, it's always in Kelvin. Kelvin is our base measurement we want to go from. And then they take both of these and they quadruple them, T to the fourth, and subtract them, and they get a net temperature change of a really big number. I'm not going to try to read it off, but there's the number you guys can get if you type it in your calculator just the same. Now that we know what this temperature change is, we can plug this part in for there, and that becomes a lot easier from this point forward then. With this then, here you can tell, okay, what they're doing here now is they're showing us how they're calculating the power. This is the number we had on from the other side. And they've put in the missing information. This is the emissivity of the skin. This is the area of the skin. And then this right up here is Stefan's constant. When we multiply this all together, we find out that the power that's being supplied by this person is 103.92 watts. Kind of takes you back to what was the movie that was really popular? The Matrix, where the humans are being harvested for the power to supply all the machines their energy or their power that they need. But this person is supplying 103.92 watts of power. So now we combine that into our energy equation to find out how much energy is being given off by this person during that 15 minutes. It was 103.92 watts times 900 seconds, and this person puts off 93,500 joules worth of energy during that 15 minutes. Well, hey, I hope this has been informational. I know you're going to have some struggles with it, but that's okay. We'll be there to help you. I'll see you guys on the flip side.